Cool. Well, hello everyone. Welcome to Public Open Evening at the Institute of Astronomy. We have some pretty clear skies by the looks of it, so we're going to be doing an evening in two halves today. First of all, we're going to have a talk from one of our researchers, and then we're going to go live to stargazing, where I think they have some very nice views of Jupiter, Saturn, and Mars lined up. Before that, I'm very happy to introduce our headline speaker, Sergio Martin Alvarez, who is going to be giving us a brief history of the universe. Over to you, Sergio.
Thank you. Let me share my screen. Can you see it?
I can. It looks wonderful, yes.
Okay. Cool. So thanks everybody for tuning in. I want to start sharing with you an extremely fascinating fact about our universe, right? I'm still fascinated by this idea even after thinking about it for a long, long time. And it is the idea that when we walk outside and we lift our gaze up into the night sky, we're effectively looking back in time. The stars that we see, the galaxies that we look at, they were shining in the past, right? And the reason we see the light now is simply because it took vast amount of time to travel down to our eyes. So it's kind of funny because we go about our daily lives and we tend to forget how small we are. We tend to forget that the universe is vast, right? And the evidence is just written up there for everybody to see. So our history, not as individuals, but as humanity, future and past, is only a small fraction of what the universe is. Not only that, of what the universe was and what the universe will be. I'm actually going to talk about that for you tonight. I'm going to tell you about the humbling idea of the universe history, right? The universe beginning, the universe evolution, and potentially what is the fate of the universe. So once again, what is the history of our universe? And we're going to start from the very beginning. We're going to start from how the universe began, the Big Bang. And when we talk about the Big Bang, we don't talk about a specific moment in time or a specific location in space, but we think that out of nowhere, the universe has suddenly bursted into existence, right? And this primordial universe, this initial universe, was characterized by three main things. It was full of energy, a huge amount of energy everywhere. It was governed by a unified force that governed everything, and it was expanding. Expanding meaning that it was fairly small, but it was increasing its size. And as it increased its size, the energy was distributed into a larger volume and the temperature decreased. And this is a constant through our universe. So as this happened, the unified force separated into the different forces that we know nowadays. But suddenly something funny happened. The universe inflated. In this inflation, the universe transitioned from the size of an atom to roughly the size of an orange, right? Unfolding into what we understand nowadays as space and time. And in this process, the universe decreases temperature down to 10 followed by 27 0 degrees, which is extremely hot still. But what's going to happen now as our universe unfolds and grows in size is that we're going to reach the next level in this ladder of complexity that we're going to build. So what's happening now is that our initial energy that was only stable as energy is going to be able to form particles, right? At the beginning, these particles are not going to be very stable, but as the universe gets colder and colder, at some point, this energy is going to be able to stay in the form of particles for longer periods of time. So now we're forming our first quarks, our first electrons. And these quarks are effectively in groups of three, what comprises all the matter that surrounds us, right? Like effectively everything around us is just made of the quarks that were generated at the beginning of the universe. But all together with this normal matter that we're familiar with in this early universe, right? That once again was everywhere. We also had this other component that I'm sure everybody's heard the name of, but don't really know what it is. So this is antimatter. And when we talk about this other matter, this other antimatter, it's effectively, you can understand it as something extremely similar to matter, with very similar properties, but with the difference that when a particle of matter and a particle of antimatter meet each other, they annihilate and they release energy. So there was this really small imbalance at this very early stage of the universe, which is somewhat funny, right? For every 1,000 million particles of matter and every 1,000 million particles of antimatter, there was an excess of one further particle of matter. And as this annihilation proceeded and all the particles of matter and antimatter kind of killed each other, everything we're left over with is only matter. And this is, we're actually, all the matter around us, ourselves, we're actually the leftover of the generation of matter and antimatter at the beginning of the universe. So we're kind of a bit of a remnant. But the universe throughout this process continued expanding once again. And what happened was that we formed the first particles that of matter that remain for a longer period of time, protons, electrons, and now we have a lot of light rays also being trapped in this soup of particles. And we reach a universe that can be considered, compared with the previous universe, it can be considered as a cold universe. And we're talking temperatures of 10 followed by 13 0 degrees. So it's extremely hot still. So we reach the first second of our universe, and between this first second and the first 3 minutes, we're going to form the first atomic nuclei. We're effectively going to form the recipe, the components of our universe. And we can measure the composition of our universe. And here, I'm showing you the first proof that I'm going to give you tonight about this history that I'm talking about, which is the chemical composition of the beginning of our universe. So there is proof for all these things that I'm going to be saying. So a funny thing that's happening now is that there is a lot of light rays in this soup of particles, and they can try to travel for small distances, but they effectively collide with electrons, with protons, and they are trapped in their neighborhood, right? In this soup of what we call plasma. But as the universe keeps expanding now for 300,000 years, it becomes cold enough that the electrons can be trapped by the atomic nuclei, right? Like these negatively charged electrons are going to be attracted by the positively charged nuclei, and they're going to be trapped in there. And effectively, as the charged particle disappears, what happens is that the light rays see a universe that becomes transparent to them, and they can get to travel for extremely long distances. In fact, they are streaming for such long distances that these light rays, or photons as we tend to call them, we can see them today still. They are what we call the cosmic microwave background. And here I'm giving you the image, one of the images that we have of the cosmic microwave background. This is an extremely important piece of knowledge for humanity. In fact, it got Penzias and Wilson in 1978 the Nobel Prize for its discovery. And effectively, this light is the remnant light of the beginning of the universe, the Big Bang, and it's extremely studied in cosmology. So that's light on one side, but obviously we also care about matter, right? And this matter that I was talking about keeps evolving, all together with this other fancy component, which we call dark matter, and it's much more abundant than matter. I'll talk about dark matter later on, but the whole idea now is that gravity is the most important driver about what's happening in our universe. And it forms this filamentary structure that you can see in the video at the moment. And in the densest regions where these filaments meet, we're going to be able to reach the next step on this ladder of complexity that we'll building up. So the very first component, the very first chemical component that we form in our universe, this simple chemical composition that I was talking about, is hydrogen. And in these regions, due to gravity, huge amounts of hydrogen are collapsing. And we're finally reaching temperatures that we can consider cold even for like this week, right? Like we're talking minus 200 degrees here in the center of these clouds. So what's going on in here is that as density increases, the temperature decreases, you can pack more and more material in these clouds. But at some point, the energy loss is not too high. So we're kind of hitting a wall in the chemistry of our universe, in the physics of our universe. But something funny happens now, and it's the atoms become cold enough that they can trap other atoms and form molecules. And the funny thing about molecules is, first of all, that you can have more stuff in less space, so you can keep increasing the density, and they also rotate, they vibrate, and that actually reduces the amount of energy they have. So what's happening now is that you can pile up more and more stuff in the same region of space. In these giant clouds, the core is collapsing, it's increasing its density, and it increases its density to a point that friction, collisions between particles, it increases the temperature. But even though there is this force outwards, gravity is so strong in the outskirts of the cloud that it keeps falling into itself. It keeps pulling stuff towards the center. So even though the cloud doesn't know it, it keeps collapsing into this very core that is reaching extremely high temperatures, extremely high densities. And at some point, atoms are going to be able to collide with each other, to merge with each other, and they're going to start up the process of fusion. And what fusion does is that it releases a huge amount of energy. And at some point, from the very core outwards, the entire cloud deflagrates. It just kind of bursts into this plasma flame, and it forms the first stars. Actually, these stars shine in the same way, fueled by fusion, as stars as our sun does today, right? This actually got a Nobel Prize to another guy in 1967. So it's important stuff. And if you remember what happened in the early universes, once again, that all the light that was being generated escaped for vast distances. So our universe wasn't generating any neon light. So this first generation of stars is illuminating our universe once again. And in the same way that the light from the sun feels warm on our skin and it warms us up, these stars were warming up our universe. We were generating this process that we call reionization. And it follows a very specific pattern. When we look up into the night sky, we can look at what is the temperature of the universe over time, and how compare that with how our models predict it to evolve in this Big Bang picture of the universe. And it matches perfectly. We can see how this reionization process evolve in our universe, right? So we have these first stars, once again, warming up our universe. So these stars are being formed everywhere in the universe, right? These clouds are being formed all over the place. And once again, gravity comes in, and what it does is that different clouds with stars, with gas, with dark matter, so on, attract each other, and they merge with each other. And they start to form these objects, these systems that we tend to call protogalaxies. And the name kind of gives it away, right? What's going to happen is that as they increase in size and so on, they're going to form galaxies. And when we talk about galaxies in astrophysics, we distinguish three main types. We distinguish elliptical galaxies, spiral galaxies, and irregular galaxies, which is just based on how they look. There's other classifications, but I think this is the most illuminating one. So we can study the formation of galaxies through computer simulations, as the one you're seeing in the video here. This is, for example, a spiral galaxy, very much like our Milky Way. And the reason I'm showing this video is not only because you can see that galaxies once again form through small pieces of gas, stars, and so on that merge with each other and grow in size, but also because looking at spiral galaxies like this one, we actually discovered the first proof of the existence of dark matter. So the idea is the following. When we look at these things, when we look at these systems, using gravity, we can measure how much mass is at this inside a given region due to the velocity that you require to orbit, to rotate around it, just not to fall into the center. So effectively, you can use the velocity of a given piece of gas to measure what is the mass inside it. And when we look at galaxies around us, when we look at spiral galaxies around us, what we saw is that there was a lot of mass that we were not seeing. Given that we couldn't see this mass, we called it dark matter. It's not the most illuminating piece of evidence, but I'll give you more later on. So on bigger scales, galaxies are also being attracted by gravity, falling into the densest regions of our universe, and they're forming groups of galaxies. They're forming what we call clusters of galaxies with several hundreds, even thousands of galaxies. And in the very center of these monsters, we're gonna form merging galaxies with each other, the most giant elliptical galaxies that we know exist. So something important, I guess, to this point from the talk is that the universe forms in this bottom-up process, meaning that once again, we form smaller things first, then we put them together into stars, into galaxies, into clusters of galaxies, so on. So we start with the smaller things and go up into the bigger ones. And I'm going to show you this video put together by the Sloan collaboration. This is a collaboration of telescopes that opened every night and took pictures of galaxies every night. And so these pictures that you're seeing here are real galaxies in their approximate location around us. I think the Earth is supposed to be down there somewhere. But if you look at this video, you look at the distribution of galaxies, something funny is that once again, you see this kind of filamentary structure that I mentioned before. So this is once again a proof of the existence of dark matter, because when we do our numerical models, when we do our calculations, the only way we can reproduce this type of structure for our universe is by having dark matter in it. The only way we can reproduce the structure that we see for our universe topologically, mathematically, is with dark matter. But that's not the reason I'm showing you this video. I'm actually showing you this video because I find it extremely illuminating regarding how immense the universe is. So this is only showing the local galaxies around us. And if you look at this, the amount of space between galaxies is much larger than galaxies themselves, which are much larger in general than our own galaxy, which is much larger than the spiral arm where the sun is, which is much larger than the solar neighborhood, which is much larger than the sun, which is much larger than the Earth, which is much larger than this country, which is much larger than our city, which is much larger than the building you guys are sitting at, which is much larger than every single one of us. So if you stop for a minute and try to imagine all these scales, it's just impossible to conceive how vast the universe is. And this Laniakea thing is actually the last piece of the puzzle that we got recently. This is everything that gravity pulls together around us that is bound together by gravity. So this is the last kind of piece of our address in our neighborhood. So that's up in the biggest scales. But if we go back to the very first stars that were formed in our universe, they are probably long gone by this point. And so you guys might know already, when stars effectively run out of fuel in the very cores, they just go with a bang. They explode in what we call supernovae. And what was happening before is that due to the fusion process, hydrogen was being crafted into more complex elements. We're talking things like carbon, nitrogen, iron, and so on. And not only they actually get these elements back into their surroundings in galaxies, but also when these stars die, they leave behind extremely interesting objects. I'm sure there's going to be more talks about them in the future. We're talking things about white dwarfs, neutron stars, or even the extremely famous, and I guess you guys might know that this year these things actually got a Nobel Prize. We're talking about black holes, right? We're talking about these objects so massive that they bend space and time, and they make it so bend that not even light can escape from them. Not even light can escape from the gravitational pull. And once again, they got a Nobel Prize this year for their prediction of the formation, but also discovering that in the very center of our galaxy, there is a supermassive black hole. And these supermassive black holes are extremely fascinating because they not only bend space and time, but they can also throw jets of material, extremely hot material, to distances much larger than galaxies themselves. So they're really cool things indeed. But if we go back to stars, right, the explosion of stars, the crafting of all these complex elements in stars, and their return to the medium of galaxies is gonna yield the next level of this ladder of complexity that once again we putting together. So what's happening now is that all these complex elements are gonna be thrown into clouds of gas that are gonna start to collapse once again. And this time they're gonna form what we call protoplanetary disks, right? And actually using the ALMA telescope, I would say recently, but I think it's been like 6 years ago now, this is the ALMA telescope. We took this picture that you're gonna see in a second of a protoplanetary system. So we've seen these things. And what they are effectively, it's a disk of gas comprised of these complex elements that once again in the very core, in the very center, is gonna undergo this runaway collapse of material. It's gonna form stars that are gonna illuminate this disk of material. But now the difference is that there is these complex elements that are heavier, that are capable of collapsing into small specks of dust that effectively are going to merge with each other to form tiny pivos that are going to coalesce to form tiny rocks that are going to keep colliding with each other due to gravity to become bigger rocks, to become effectively protoplanets, which effectively are going to continue evolving to become round, to clear their orbit, which is what we actually define as a planet. And when we talk about planets, there is so many types, so many. You can imagine giant balls of gas, cold ones, hot ones, rocky planets, ice moons, so on. The list is immense. And this video you're seeing now is all the exoplanets in their different systems that the Kepler telescope discovered back in 2012. But nowadays we're talking about more than 2,000 planets confirmed outside of solar systems. So there's a lot of them, a lot of them. And actually last year there was another Nobel Prize given for the discovery of the first exoplanet. And at least in one of these planets, we are fairly certain that we got all the elements to reach the next level of this ladder of complexity, right? You had meteoric membranes, you had liquid water, you had an energy source, you had a stable planet for a long period of time, so on. But I'm not going to talk about life tonight. Actually, I'd rather finish the talk talking about death, and more specifically, what is going to be death of our universe. Once again, this is going to go back to the idea that our universe throughout its entire history has been expanding. And it hasn't expanded in a random way. It actually does in an accelerated expansion. When we talk about the expansion of the universe, it's not expanding into anything. It's more the idea, you can imagine a rubber band. When you stretch it, it takes more space. It's kind of like space is popping up in between space. But once again, this expansion is accelerating over time. This actually got, in 2011, Perlmutter, Rees, and Smith, he actually got them a Nobel Prize for discovering that the universe was expanding in this way. So what these three guys did, up here in the upper right corner, was look at how stars exploded and use that to measure how the universe was expanding. The idea is that generally we think that some type of stars explode with the same shining all over the evolution of the universe. Therefore, if you look at stars back in time, they should have less and less brightness depending on how big the universe, how big the distance towards them is. So using some fancy physics, you can translate this into the composition of the universe. And we've measured the composition of the universe. And roughly is 5% is all this ordinary matter that we're all familiar with. There is this extra 25% of this weird stuff that was causing all the collapse of material, right? This dark matter that was governed by gravity. And there is a 70% of we have no idea what, which is pushing the expansion of the universe. And we call that dark energy. So this composition translates into the shape of the universe. And when we say the shape, we're actually talking more about how space distributes with respect to space, or how space relates with more space. But there is effectively three shapes. It can be open, closed, and flat. An open and a flat universe are fairly similar. The idea is that everything's going to expand forever, faster and faster in an open case. It's going to slow down in a flat case, but every single particle is going to end up isolated. And then you can have a closed universe, which is one in which the expansion effectively at some point stops. Gravity starts to govern everything and pulls everything together back into maybe the same point in space, but then our physics break. So we've measured this. We actually have measurements of what is the shape of the universe, and it is in this graph that I'm showing you now. And I guess it's a bit opaque, so let me translate it a bit. The idea here is that our universe can either be flat, it can be closed, or it can be open. And once again, we have measurements of this, and if I can translate this a bit further, the answer is actually something that we tend to find when we look at all the big questions of humanity. Our universe seems to be pretty much flat, maybe open, and possibly closed. What does this mean? This means that once again, we have no idea. And if there's any young people amongst the audience tonight, we need you to come and help us figure out the answer of what is the fate of the universe. Thank you everybody for listening. I don't know if there's any questions, but I'll take them now. Cheers.
Cool. So we have so far we have a comment and a question. So Sergio says congratulations. Capsy asks, how many atoms are there in the universe? Nice easy question for you.
I have really not even a conception of that. It's already hard. We conceive the universe having an infinite number of galaxies. We conceive practically for us, right, in our minds, the number of stars in a galaxy is almost infinite. The number of atoms in each of
I've heard 10 to the power of 80 being like an estimate for the number of atoms in the observable universe.
I'll believe you.
I mean, 10 to the 80 is a pretty big number.
It's pretty hard to conceive.
Absolutely. Sebastian says, thank you for the talk.
My pleasure.
Cool. So if there are no more questions, going to hand over for the second half, and I have my fingers crossed that it's still clear. I'm going to hand over to Paul and Brian of the Cambridge Astronomical Association, who are giving me the thumbs up and telling me that we are going to be able to do some stargazing. Yeah, we'll have to do a virtual round of applause for our speaker Sergio, and I will hand over to our stargazers, Paul and Brian. Over to you guys.
Well, thanks, Matt, and thanks, Sergio, for a fantastic talk. The good news from our side here is that I've got a completely clear sky, which is quite an unusual thing for a Wednesday night. So without further ado, I am going to attempt to show you what I can see with the 14-inch telescope that's behind me, and also with the all-sky camera. So I'm just going to pop out on the all-sky camera a moment, and then my partner in crime, Brian Lister, is going to give us a little bit of a commentary on things as I organise for them to be shared. So we're going to go over to the all-sky camera, just so you can see an overall view of what's going on the sky. So you should be getting it now. So we can see some stars there, Brian, and low in the south I can see down here I can see Jupiter. This is where my telescope is pointing. There's Jupiter, look.
Yeah. And where's Mars?
Mars is actually right over on the horizon to the side, and it's just behind the tree at the moment, but in a few minutes it's going to be visible. So we'll go there just once that's cleared.
Okay.
We've also got Saturn, which is just to the left of Jupiter here. And I can see Cygnus up here. We're also going to look up there, aren't we?
Yes, at the Alberio, and a coloured double star. Right, we'll go with Jupiter.
Okay, so we'll come back to the main screen for just a moment. And I'll share what the telescope is seeing rather than what the wide camera is seeing. And you should have that on your screens now. So
okay,
here we have it. Brian, over to you.
Okay, first, we're looking through a lot of atmosphere. We're looking obliquely through the atmosphere. So Jupiter is not very clear at the moment, and there's a lot of high cloud at the moment. So you can see that Jupiter isn't round. And that's because it spins so rapidly. And we can't see any markings on it yet. Paul may try jiggling the image a bit to see if we can see the cloud belts, which are usually apparent even in quite a small telescope. But tonight is going to be difficult because of, as I say, the misty high cloud we're looking through, and because it's low down in the sky, we're looking through a lot of atmosphere. So that does have a problem of causing the image to degrade. Right, he's adjusting the exposure to bring out the detail. Gradually making the camera more sensitive. And then
on my end, I can just about make out the two main cloud belts.
Yeah, they're going horizontally across the screen. You just have to use your imagination.
Yeah.
Just a wee tad.
It is because it's literally only 5 degrees above the horizon at the moment.
Crikey.
So there's a very large amount of atmosphere. If you look straight up, you're only looking through 5,000 feet of thick air before really there's nothing between you and space. But when you look horizontally like this, there's about 100 miles of thick air full of dust before we get a view of space. So the Jupiter's not very well placed right now.
So what we can do, if we can't get much of the surface of it, Jupiter, we could look at some of its moons. It's got 79 moons at the moment, and we could see the 4 brightest ones that Galileo saw when he first pointed the newly invented telescope in 1609, about Christmas time, during that time.
So as turn the gain up a little bit, or the exposure time up a little bit, Brian.
Yeah.
And you can just start to see a little moon there. It's about 4 o'clock on the clock face. That's Ganymede about to disappear into eclipse.
Right.
If I bring the, I'm going to slowly bring the brightness up, and you'll probably see it better now. It's right on the edge of the planet.
No,
if I turn the brightness up too much,
you'll flood the
image.
Yeah.
But can you see it now? No.
No, I'm having to keep going.
I'm going to have to go on to the new scale here now. I have to go to half a second exposure time.
You can also see the effects of the atmosphere on Jupiter. You've got a blue top and a red bottom. It's acting a bit like a prism. But now we've picked up 2 more moons.
I'm just going the other way. Can you see Ganymede now?
I'm struggling.
Just under the cursor there. I can only just see it myself.
No.
If I turn the gain up nicely, you can see the next two.
You get a little. We get a little lump now. At 4 o'clock, we've got a little lump where Ganymede is.
Yeah,
So, that's brought it up nicely, and then we've got the other two we can see. Okay, to the right.
so just 10 minutes ago, Ganymede was clear of the edge of the planet, and it swung round while we were listening to the lecture.
And it'll take an hour or two to pop round the other side.
That's right.
Right, go.
So for those two that you've got there,
Yeah.
they are Io and Europa in that order.
Right, Io is because it orbits so close to Jupiter, feels the full force of Jupiter's immense gravitational pull, and pulls it around a bit. So it keeps the planet or the moon in a warm. And there are active volcanoes on Io, and spacecraft that have gone by have actually imaged the volcanoes erupting. And it's and the planet, the moon itself, appears very yellow, and that's mostly due to sulfur. And being the closest of the large moons, the Galilean moons, the 4 moons that Galileo saw when he looked through his telescope, it will always feel the effect. It's a bit like when you get a lump of plasticine and you knead it in your hands. It's not getting hot from your hands, it's getting hot from the internal friction. And that's the same with Io, why its volcanoes keep active. And then Europa is an icy world. It's covered in ice and very smooth. There are no mountains or valleys. And you tend to find one thing that's missing from it. There are only 1 or 2 craters on the icy surface, because once a meteorite hit Europa, the ice gradually forms over it and the crater disappears. So that it's very smooth and very round. But it too also feels the effects of Jupiter. But that just leaves Callisto. And Callisto is usually quite far away. Do you know where it is, Paul?
I do, Brian. If you just give me a moment, I'll find it for you. So I've just zoomed out a bit. I'm now going to have to adjust the telescope and move it sideways to bring Callisto into the field of view. And as with everything in astronomy, I've got up, down, left and right buttons, but they really don't correspond to the right directions on the camera. So indeed, I have gone the wrong way straight away, because I need to go back this way. And if I take it so that Io and Europa are just on the edge of the screen, then there's Callisto just on the left-hand side now.
Yep, we've got it now.
Yeah.
And that orbits quite a distance away from Jupiter and doesn't feel so much of the effects. And I always think Callisto looks very much like our moon. It's heavily cratered, and it's about the same size. These four moons are roughly the same size as our moon. That's one thing about the Earth. It's got a whacking great moon. And there are not many moons bigger in the solar system. We'll see some tonight, and Titan, Saturn's moon, will also be visible. Now, Jupiter takes 12 years to orbit round the sun. So each year it moves approximately 1 constellation around the night sky. And as time goes by, it will gradually work towards the winter sky, which will make it higher. you find that planets are low down in the sky during the summer when they're at their best, and in the winter they're high up in the sky, and you can see really an enormous amount of detail. And we can even see a bit of blurring round the moons from the atmosphere. And we've lost Ganymede. That's now gone behind the planet. There's currently a satellite orbiting Jupiter called Juno. That's been in orbit for a while, and it keeps sending us detailed images of the planet's structure, because Jupiter is, or cloud belts, Jupiter is virtually all atmosphere, and maybe something very hard right in the middle, like about the size of an Earth or two. So it tends to be all atmosphere, and so all we see is this tremendous weather system that continually changes, with cyclones and of course the famous red spot. Unfortunately, we won't see that tonight because of it's so low down, but it's about 3 times the size of the Earth, and it's a storm that's been raging now since, well, the very first telescopes to look at it saw the great red spot, and sometimes it changes in color. Now I can see, yes, I can see one cloud belt quite well, the northern one, or the top one where Paul's pointing, and I can't quite see the southern one.
Just about visible.
Yeah. Oh, yeah. Yes. It comes and goes as the image improves, because this is about half a second exposure, isn't it?
Yeah, a little bit less now. I've turned it down.
Oh, right.
If I turn it up, then it washes out.
No, we can still see I can see the cloud belts better now.
Well, that's better for you, is it?
Yeah.
Okay.
Yeah. And they're the 2 main cloud belts, and the red spot would be near the lower one. Is that right, Paul?
That's correct, Brian. Yes.
Yeah. But I can't see a sausage. No.
It may well be on the other side of the planet, of course.
Yeah, the planet rotates fairly rapidly in less than half of our day. It's about 12 hours. So yes, you can see now that it's not perfectly round. It's an oblate spheroid due to the high rotation.
You can see it jumping around. That's the turbulence in the atmosphere.
So when stars twinkle, that's a bad night for astronomers. That means the atmosphere is very turbulent. It might be all very well for poets, but for astronomers, when the atmosphere is dancing about and making stars twinkle, it's not good for us.
Okay, Brian, shall I move on and try and lock onto Saturn instead?
Yep, go for Saturn.
So to do that, I have to, I'll just come off screen share for a moment. And I have to get my telescope handset into operation over here. Standing, and I just have Saturn selected. So I'm going to press go to, and we'll just see what happens. Last week when we did this, it found it straight away.
Good. Saturn is considerably further away from the Sun than Jupiter, and it takes 29 years to orbit instead of Jupiter's 12. So obviously the further you go away from the Sun, the longer the planets take to orbit the Sun. And again, Saturn has been low in the sky now for several years, and gradually over the next few years, it will start to rise into the winter sky. Then all we'll need is clear Wednesday nights. And you'll notice that Paul's telescope is quite compact. Many of you have looked through the Northumberland telescope at the Institute of Astronomy, which uses a lens, and an eyepiece is 20 feet away. Whereas Paul's telescope uses both lenses and mirrors, and means that it's a very compact telescope. It's actually just slightly bigger than the Northumberland telescope, and still has the same more or less focal length combined, sort of squeezed in that short tube. Oh yes, we've got Saturn, and we can see the rings are nicely open. And during its 29-year orbit, the rings will change orientation. It will, they'll gradually become more oblique, and after a few years you see them edge on, and then they open up the other way. And it will do that twice during the its orbit. So we see the rings, both the underside and the top side, if you like. Let's just bring it into focus. And Saturn is another gaseous planet, not quite as big as Jupiter, about 9 times the size of the Earth, and its specific gravity is less than 1. So if you could find a bathtub big enough and plopped it in, it would float. But its weather system is less distinct as seen from the Earth. We occasionally see storms and cloud belts on Saturn, but you need exceptionally good clear skies, and you need Saturn to be high up.
Oops.
Yeah, no, don't worry.
Sorry, I lost it.
Can't miss it.
Can't I see? I think my camera stopped working for a minute.
Oh,
there.
no, we got it. Yeah.
Just trying to get it a little bit bigger for you.
Okay, and then we'll look for moons.
How's that? Get that centered.
It's got over 80 moons, but of course we won't see 80. We'll be lucky to. There are usually 5 brightish ones we can see on the when we look on the Northumberland lawn when the planet is up high. But I think we'll struggle to see 2 or 3. Certainly we'll see Titan.
Okay, shall we go moon hunting?
Yes, let's go for it. You can, yeah. Going to increase. Oh, actually, we can see the rings better now. Yeah.
Is that good?
Yeah, it's good for us. Yeah, they've just gone past their widest opening at the moment. So over the coming years, we'll gradually see them turning more edge on. Okay, we'll go for Titan.
Yeah, let's go moon hunting.
This is higher up in the sky, isn't it?
Well, it's only about 1 degree higher. So it's nothing to write home about.
Again, we can see the prism effect of the atmosphere with the blue fuzzy bit at the top and the red fuzzy bit at the bottom.
So I've zoomed out a little bit, and we've got a moon, I think, there. Just off to the right. Can you see that yet, or is it not bright enough?
I can't see it on my computer.
Bringing up the brightness for you.
Yeah, got one. at 3 o'clock.
Yeah.
About 4 diameters away.
Yeah. So I think that looks to me like Titan. It's always possible to tell. It has a sort of faint yellow color to it when you observe it through the telescope, rather than being pure white. And its orbit seems to carry it about that 4 planet diameters away from the main body. So we'll claim that that's what we're looking at, I think. And I can also see some others. Can you see? No, I think this is Titan here.
Yeah, we got Titan.
I've got one here.
Woo, I think so. Yeah.
I've got another one down here.
Yeah, I can see that one. Yeah, I got there first.
Yeah, at the moment, I can see some others, but they're right on the limit of visibility. So let me see if I can figure out how to get a bit more out of this. Let's go for a slightly longer exposure. I'm going to go for 1 second.
Of course, Titan is a moon bigger than our moon, and it's the only moon in the solar system with a sizable atmosphere. And so when spacecraft visited it, they didn't see much of the surface details. It wasn't till the Huygens lander, the Huygens probe rather, visited it, we saw beneath the surface of the cloud. And there are lakes of methane. Is it methane?
Methane, yes, Brian.
Yes. Yep. And these vary as the planet goes round, or the moon goes round. These change the levels of the lake seem to change, and the coastline varies from season to season as it goes round Titan. Yeah,
Right,
we can see.
You can see a host of moons now, I hope.
Yeah, I can see 3 easy ones. And is there one down the bottom?
Titan here.
Yeah.
We have Rhea over to opposite Titan on this side.
Yeah.
I think this one down here is Dione.
Yeah.
And we've got Tethys there. And right next to the edge of the rings, just here, I think that's Enceladus.
Right.
So that's a pretty good haul.
Yeah, you've done well.
Yeah. We've got one down here, which I'm having trouble identifying. It might be a background star. I'm not sure at this point. So let's just move around. I'm going to zoom out a bit and then try panning around to see what else I can find. So you should have the entire screen visible there. I'm going to have to reduce the exposure time back down, and then try and get Saturn more back in the middle of the screen because it's rather in one corner. So needs to go down, so I shall press up and see what happens. Is that moving the correct way? No, it's not. It's going up. It's every time. Every time.
Don't worry.
We'll go the other way. And then we'll try this button and go, that's the right way. Bring it into the middle. Oh, a bit too far. That'll probably do. And then we'll put the gain back up again and see if we can just check out what's going on over this side at the sort of 9 o'clock position. Okay, yeah, there is one up at the top here.
Oh yes, we can see.
I believe that's Iapetus then.
Yeah,
So,
we can
yeah,
see the inner moons better now. Yeah, we can see.
that's really rather good, isn't it?
We've got 7. That's well done. And of course, one of the planned missions to the large moon Titan is for there to be a drone that will fly through the thick atmosphere. This drone will be called Dragonfly, and it's a project that will hopefully not be too long in coming. The funding has been got for it, so they hope to fly around through the atmosphere. Of course, the other planet we'll look at is Mars, and of course there's another drone been sent there.
Shall we try and do that then?
Yeah, we'll go for that. Is it?
I'll drop the exposure down so I've got a good view of the planet again.
Yeah.
Which always helps me when finding things. Otherwise, the reaction time of the camera is too slow. So, oops, there we go. It's gone to nothing. So there's a nice but small image of Saturn. And I'm going to try and go for Mars now and hope that it's out from behind the tree. I haven't actually looked, but let's see if we can find it.
Okay, go for it.
Here we go. So I've told it to go.
This is one area we have problems with on the Northumberland lawn when we're doing public observing. Sometimes the telescopes throw wobblies and just refuse to point in the right direction. I think we just saw Mars flit by the screen. These computer controlled telescopes are better in observatories where they remember where they are. Whereas on Wednesday nights, when we used to get them out, hauling them in and out, they seemed to get a little confused. So they didn't always point to the right object. How's yours doing?
It's pointing at it. Unfortunately, I was right. The tree is in the way.
Oh, that one must have been a street light we saw flash by then.
I'm not sure what it was you saw flashing past, but the Mars, I can see it just through the edge of the tree. But the scope can't see it because it's got a very slightly different perspective to me. So I'm afraid we'll have to leave that one for the moment.
And go for Albireo.
Let's go for Albireo. So I'll just come out of screen share for a moment. And we'll get the star map into operation.
Albireo is in the constellation of Cygnus, the Swan, and it's one of the few constellations that looks like what it's meant to be. It's a large cross it's like a swan with outstretched wings, and Albireo is its beak, and it's a double star. But it's 2 different colours of stars. Most double stars tend to be white, but this one is unusual in having stars of 2 different colours, one hotter than the other. So with stars, the colour depends on the temperature. So red stars are cooler, orange stars are hotter, yellow stars like the sun, hotter still, and the hottest stars are white. But stars can go even hotter than that. It's just like heating up a lump of iron. You can go from red, orange, yellow, white, but stars can go one better. You can go blue hot. That's stars that are about sort of upwards of 20,000 degrees. And they orbit each other about every couple of 100 years.
Okay, so the computer hasn't found this one.
Can you do it by eye?
Yeah, I should be able to.
Because it's reasonably bright.
I see it. And can see it as well, so I'll try and zoom in on it.
Okay.
The old-fashioned way.
This is not too distant star. It's about 400 light years away, this pair of stars.
I'll tell you what, I'll share the screen and you can shout if you see anything.
Okay.
Because I can't watch the screen and drive the scope at the same time.
Okie doke.
That's the output of the camera coming your way. Tell me if you see anything.
Yeah, we will. Nothing at the moment. The beauty is I'm sitting in nice and warm and Paul's wrapped up well because an observatory works best when it's cold. Yes, here it comes.
There we go.
Yeah, it's slightly out of focus, which will do us well because when a star image is out of focus, it shows the colors, and we can see that there's a blue star top left and an orangey colored star, a yellowy star, and they're different temperatures. Now, as he brings them into focus,
I was just trying to center it up now, Brian.
Okay.
Before I try anything complicated like focus.
Yeah, the yellow star is just a bit cooler than our sun at about just over 4,000 degrees. And the blue star is about 12,000 degrees. So you can see it's considerably hotter.
Okay, so there we have it in the middle. Yeah, the colours are looking really rather nice there, aren't they?
Yeah.
So let's try a bit of focus, shall we?
Yeah, go for it.
That's the wrong way, isn't it?
Yeah.
We'll go the other way.
Colours are good now, but we might lose the colours as they get sharper. There we go. That's them in focus. You can see that the yellow star is in fact brighter than the blue star.
So I think that's probably in focus. What I normally do at this point is I've got the trick diffraction mask, which I put over the front of the telescope.
Yeah, and that splits the colours up, does it?
And it splits things up. That's me moving the telescope, causing that psychedelic effect. But what we should get with the mask on there, when it settles down.
Yes, we're getting the colours very well. Yeah, brilliant.
Yeah, that's quite good, isn't it?
Yeah.
Now, what I have noticed, looking out of the dome window is just how much cloud is coming over.
Well, shall we have one last go for Mars, or call
No,
it a day?
no chance, I think, because that's where the cloud has come from.
All right.
We can't do that.
So we'll have an early night then.
So unless we could possibly try just one object that's not too far from here, which is M13.
Yes.
I think then we'll have to call it a night. And even that, I'm going to be racing against these clouds that are suddenly appearing.
Okay.
So I'll do that, and I'll leave the screen on and see if I can do this as quickly as I can.
Yeah. What he's going for is, what Paul's going for is a globular cluster. It's a star cluster that's outside our galaxy. There are about a couple of hundred of these, and they hover, they're in orbit around our galaxies, a bit like sort of bees around a honey pot. And these globular clusters are a very high concentration of stars, a great ball of stars, which I'll hope we'll see. And the other sort of cluster, the clusters we see in our galaxy, are open clusters, which are just less dense and random in shape. And this is, globular clusters tend to be very old. And this one is cracking on for 12 billion years old. So not quite, formed very early on in the age of the universe.
Now, I've been beaten to it by the cloud, Brian.
Bad luck.
It's now almost completely covered just in those few minutes. So, yeah.
Bad luck, never mind.
Oh, well.
We'll call it a night. And we'll pass back to Matt.
Cool. Well, thank you so much, guys. I expect this afternoon, when it was pouring down with rain, I expected no observing at all. So even to get some is nice. I always love whenever I see double star Albireo, or it reminds me of this time of year. It's a kind of a nice kind of autumnal feel, isn't it? Having Albireo in the sky.
Yeah, it's a good one to go for.
Cool. And thank you so much to everyone at home. Hope you enjoyed this second Wednesday evening. For the time being, we are doing these as remote evenings. We will go back to doing them face-to-face as soon as the current unpleasantness returns to normal. But for the time being, we'll be doing them all online. You can join us every Wednesday evening. And next week, we have another talk from one of our researchers talking about observing the dark universe. I do also want to point out, on our YouTube channel, we have a special guest speaker next week. Professor Emily Levesque from the University of Washington is coming to give a special talk called The Last Stargazers, which is all about the life of a professional astronomer. And that's going to be next Tuesday at 7 p.m. UK time, right here on the YouTube channel. So yeah, if that sounds interesting, come check it out. And we will see you guys next week.
Bye.
Bye.